All right, welcome back, everyone. For the stats majors and focused learners joining us today, get ready because we are diving into a real masterclass. In this explainer, we're embarking on a deep dive into the quest for computational efficiency in variance estimation. We're going to explore how statisticians actually wrestle with massive, complex survey data to find standard errors. We'll be moving all the way from the brute force resampling of the Bootstrap method right up to the really elegant modeling of generalized variance functions. So if you've ever wondered how government agencies handle the crazy math for thousands of published estimates, well, you are absolutely in the right place. Let's get started. Okay, let's dive into this roadmap. Here is our syllabus for today. 1. The Bootstrap method. 2. Stratified multi-stage bootstrap. 3. Creating replicate weights. 4. Generalized variance functions. 5. GVF pros and cons. And finally, 6. Constructing confidence intervals. Section 1. The Bootstrap method. At its core, bootstrapping kind of flips traditional inference totally on its head. It does this by treating your sample as if it were the entire population. From this pseudo-population, we draw resamples with replacement. We rely on the empirical probability mass function because it closely mirrors the true population distribution. So let's look at the actual bootstrap variance formula on the screen here. V sub b of theta hat equals 1 over r minus 1 multiplied by the sum of those squared differences. Look closely at the terms inside the parentheses. Theta hat r star is the estimate calculated from a specific rth resample. That little asterisk explicitly denotes that it's a bootstrap statistic. We subtract the mean of all the bootstrap estimates from it. The absolutely crucial element here is R, right? That represents the total number of bootstrap resamples drawn. You're literally calculating the sample variance of your resampled statistics. To kind of ground this, let's look at example 9.9 straight from our textbook. Imagine we draw a simple random sample of 200 heights and then draw resamples with replacement. Looking at these resulting frequencies, you can actually see the empirical probability mass function taking shape across all those iterations. Look at that heavy concentration right around the true median of 169. What we're doing is physically building the sampling distribution of the median frequency by frequency. It's like a giant puzzle coming together. But here is the kicker. To get that stable variance estimate of 0.9148 that we see in that example, we didn't just run this a few times. We ran R equals 2,000 iterations. 2,000! This really highlights the sheer volume of computation required here. Bootstrapping relies heavily on the law of large numbers kicking in, which, as you know, demands some serious brute computational force. All right, moving on to Section 2, Stratified Multi-Stage Bootstrap. Now, simple resampling completely breaks down out in the field because it destroys a survey's complex design structure. To fix this, we turn to the rescaling bootstrap developed by Rao and Wu. Here is their three-step process. First, within every single stratum, we independently select a simple random sample of n sub h minus 1 primary sampling units or PSUs with replacement. And there's a massive rule here. Observations within a selected PSU are always kept together. You cannot split them up. Second, we create a replicate weight factor for that specific resample. And finally, step 3, we use those adjusted weights to estimate our variance. Let's actually break down the math for step 2, the Rao-Wu replicate weight formula. This tells us exactly how to rescale. The new weight for an observation in replicate R equals its original weight, Wi, multiplied by a scaling factor, which is NH divided by NH minus 1. That NH minus 1 is a really critical bias correction factor. It ensures the variance estimate remains unbiased for the complex design. Finally, we multiply all that by MHJ superscript R. That is simply the number of times that specific PSUJ was selected in this replicate. If it wasn't selected at all, well, that multiplier is 0, and the weight just zeroes out entirely. So as statisticians, we always have to weigh our tools objectively, right? The primary advantage of the Bootstrap over methods like jackknife or balanced repeated replication is its incredible flexibility. It works beautifully for general sampling designs and, crucially, for non-smooth functions like quantiles and medians. But the massive disadvantage? The computational burden. I mean, running thousands of iterations on a complex multi-stage survey can be a really huge lift for standard processing power. Which brings us to Section 3, Creating Replicate Weights. How do we actually package this computational power so end users can analyze the data without needing a PhD in survey design? We use a rigorous 4-step pipeline for survey weight construction. First, you choose your replication method, so Bootstrap, Jackknife, or BRR. Second, construct your original base weights, which are really just the inverse of the selection probabilities. Third,
Generate your columns of replicate weights using the math we literally just discussed. But step 4 is absolutely critical. You must apply all post-stratification and non-response adjustments independently to every single replicate weight column. This is what ensures your variance estimates accurately capture the variance reduction provided by those specific adjustments.
And the brilliant payoff of this pipeline is that regardless of whether you used Bootstrap, BRR, or Jackknife, the end-user variance calculation shares just one general replicate variance estimator form. The variance of theta hat is simply the sum over R replicates of a coefficient CR multiplied by the squared difference between the replicate estimate and the full sample estimate. That CR factor is like conceptual glue. It changes depending on the method to scale the variance properly. For BRR, it's 1 over R. For Jackknife, it involves n-1. But for our Bootstrap method, that CR coefficient is strictly 1 over R minus 1. So the survey agency does all the heavy design math behind the scenes, and the analyst just runs this one unified formula.
All right, let's pivot. Section 4, Generalized Variance Functions.
So what happens when calculating even this streamlined variance becomes an insurmountable macro-level challenge? Imagine you're dealing with massive government data sets like the current population survey. They are publishing hundreds of thousands of estimates every single year. The core dilemma here is, how do agencies publish all these thousands of estimates without running millions of Bootstrap iterations or without supplying public use files packed with thousands of unwieldy replicate weight columns? Honestly, it would be computationally and logistically overwhelming for everyone involved. The answer they came up with is a brilliant mathematical shortcut, the GVF regression model. Instead of simulating the variance directly for every single variable, statisticians model the relative variance, which is denoted as V sub I. Now, why relative variance? Well, because the relative variance, which is just the coefficient of variation squared, often exhibits a much more stable, predictable relationship with the size of an estimate than absolute variance does. They postulate that this relative variance is equal to an intercept alpha plus a slope beta divided by the estimated total, t hat I. Essentially, we are mapping the mathematical relationship between the size of an estimate and its variance. And this brilliantly illustrates the real power of GVFs. By doing a little bit of algebra, we convert that relative variance model back into an absolute variance model. V hat of any new total equals A times the total squared plus B times the total. Those A and B values are estimated regression coefficients provided by the agency. They act like a shortcut key for the user. Once the agency publishes those parameters, an end user can instantly calculate standard errors for literally any new total using basic middle school algebra. No resampling required at all. Boom! So, how does an agency actually derive those A and B coefficients? They follow Valiant's 4-step algorithm. Step 1, they do the heavy lifting. They estimate direct variances using replication for a specific subset of K key totals. Step 2, postulate the relative variances model. Step 3, run a weight of least squares regression on those K estimates to find the A and B coefficients. They actually give more weight to items with smaller relative variance here. Finally, step 4, use that smooth, flexible regression function to predict the variance for any new statistic you want.
Section 5, GVF Pros and Cons.
Just like with bootstrapping, we have to objectively analyze these trade-offs because GVFs are, at the end of the day, approximations based on assumptions. On the plus side, GVFs offer massive time savings. They speed up annual reporting and allow analysts using public use files to easily calculate standard errors, even when underlying design data is suppressed for privacy. Plus, because it's a regression line, it actually smooths out anomalous item-to-item fluctuations that you get in direct variance estimates. But the disadvantage? Well, if a specific subpopulation has a highly clustered design effect that wasn't captured in the model's base variables, your GVF standard error might be wildly inaccurate. Specifically, it might severely underestimate the true variance, which is a real danger. Finally, Section 6, Constructing Confidence Intervals. Getting the variance is only half the battle. We actually need to apply it. The most common method is the normal approximation. Because the central limit theorem is operating under complex survey conditions, our parameter theta hat asymptotically follows a normal distribution as the sample size grows. So an approximate 95% confidence interval is simply theta hat plus or minus 1.96 times the square root of our estimated variance. That 1.96 multiplier is derived directly from the z-distribution for a 95% two-tailed test, which I'm sure you guys have seen a million times. And that variance, of course, comes from either our replicate weights or our GVF model. But, and since you are stats majors, you know this, you can't just blindly multiply by 1.96. This assumes a few rigorous conditions.
First, the parameter must be a smooth function of population totals. Second, it needs continuous second-order partial derivatives. Third, a sufficiently large number of PSUs must be sampled to ensure that asymptotic normality actually takes hold. If these rigorous prerequisites aren't met, say you're calculating a quantile or you have very few PSUs, well, the normal approximation completely falls apart.
And that is precisely where the Bootstrap method swoops right back in as the hero. If you violate those normality assumptions, you can bypass the approximation entirely. As we saw in our R-code examples earlier in the textbook, you simply sort the array of your thousands of Bootstrap iterations and extract the 2.5th and 97.5th percentiles directly from the list. This gives you a perfectly valid equal-tail confidence interval drawn straight from the empirical sampling distribution. It is direct, it's empirical, and honestly, it's just elegant. Which leaves us with a really fascinating tension to consider. We developed generalized variance functions in the first place because direct resampling was just too computationally expensive to distribute at scale. But as raw computing power continues to grow exponentially, moving from old mainframes to the cloud, will we reach a point where brute force bootstrapping becomes so fast and trivial that elegant statistical shortcuts like GVFs are rendered completely obsolete? It's a provocative question right at the frontier of survey methodology. Think about that as you continue your statistical studies. Thanks for joining this explainer, keep questioning the data, and we will see you next time.